Okay, we are going to start this chapter 2, so derivatives, and we're talking about vectors. So this is the typical picture of a function. We talked about this already, but we have a function which takes elements, inputs, and gives you outputs. And 2 is the codomain. And the function is often spoken of as a rule, or a way of tells you which this element goes to where. So that's the rule. And here we have the notation that says that it takes elements from set X and outputs elements from set Y, or points to elements in set Y. So we can say like a social security number is a function which goes from the set of US citizens to a bunch of numbers. So X doesn't have to be a numerical set, although for us it usually will. However, in this example, the set of US citizens is the domain. Another example is assigning dorm rooms to students. So then you would have students and dorm rooms as the two sets of students and sets of dorm rooms. And the concept of the range, I guess, I think the codomain is the set of all possible, I always get this confused, but the set of all possible values, and then the range is here, the set of y in y, such that f of x equals y for some x. So the range has to have, so you might have a whole lot of y's here, but only some of them get actually hit by values from the domain. So the ones that actually get hit are called the range. And that's what this definition says. Okay, we also have a word called onto, or surjective. So if that means if every element in Y is the image of some element of X, that is, if the range of F equals all of Y, it means every element in Y gets hit by something. So they say the social security function is not onto, since this is in the codomain but not in the range. So nobody, I guess, has this number. Okay, then we have a concept called one-to-one, or injective, and that means that this doesn't happen. What I mean is, here we have this element going to here, and we also have this element going to here. So that means they're both going to the same Y element, and that's not one-to-one, or that's not injective. So they say a function is called one-to-one if no two distinct elements of the domain, so two distinct elements here of the domain, have the same image. We say this is the image of this. We say this is the image of this. So if no two distinct elements of the domain, here and here, go to the same element in the range, then it's called one-to-one. So this is not one-to-one, because we have two distinct elements going to the same one. And more formally, we say that is f is one-to-one if whenever x1 and x2 are in the here and they are not equal, then f of x1 cannot be equal to f of x2. If that's true, then this is called one-to-one, or an injective function, or one-to-one function. So again, this is one-to-one, but this is not, because there are two going to the same one. Okay, let's take in a simple example. X squared, the domain and the codomain are all of R, so we say that it's all of R and all of R. But the range, so the codomain is all of R because that's what they said it was, but actually there's no Y values that are negative. You never get a negative value from this, so nothing, the outputs are never negative. So the range is only 0 to infinity, so it's only non-negative. So f is not onto because we specified that now I get confused, that the codomain is R, but the range is not all of R. So not all of the codomain gets hit. Okay, also note that f is not 1 to 1. For example, both, if you put in 2 and negative 2, that's in the domain, right? You can have negative numbers in the domain. You can't have them in the range. Or you can have them in the range. But anyway, if you put 2 and negative 2, they both get mapped to 4. So, but 2 and negative 2 are not the same. So we have two different elements in the domain going to the same element in the codomain. Okay, and here's another one. You can read this. Okay, now we're ready to think of functions of more than one real variable. So we can talk about functions from that are vectors. So in an n-dimensional vector or an n-dimensional space, and getting mapped to vectors. We said in class that when this is more than just R, so if it's R2 or R3 or anything, then we capitalize this when this one is more than just R. Okay, so here is a function called t, which goes from R3 to R. So it's a scalar valued function, as we said. So it takes 3 values as input, so we can say the elements are from R3. The input is from R3, but the output is just a scalar, just this stuff. So they say we can think maybe a temperature function. So x, y, z is the coordinates of a point in R3. So it's the coordinates in space. And then this gives us, depending on the coordinates, we get a certain temperature out according to this formula. So for example, at 0, 0, 0, it's 0 plus 0 plus 0, but at 0, 0, 1, it's 0 plus, no, that's still 0, and that's still 0, so it's still 0. At, let's say, 0, 1, 1, so this is 0, this is 0, but this is 1. So it would be maybe 1 degree at that location. Okay, here's another example. That was called t. Notice it's not capitalized because this is not more than R1. This is called L. This is also not capitalized. So L takes a vector from Rn and gives us the magnitude of that vector, which is just a scalar. So this is a length function in that it computes the length of any vector in Rn. And then they say, note that L is not 1 to 1. For example, these two, remember this means one of the basis vectors, and this is a different basis vector, but L will take both of them to 1, even when they're obviously not the same basis vectors for any two standard basis vectors. L also fails to be onto rather. The length of a vector is always non-negative, so so negative values are not being hit. Okay, now suppose we have a vector as an input, but notice this is bold, so the output must be a vector, not just a scalar, according to what I said about the notation. So what is that true here? So we're doing this. Remember, this gives us, this normalizes, this creates a unit vector, or it's also called normalizing the vector. So this creates a unit vector. So you can see that we're dividing by a length, but that's that doesn't change. So this is a vector divided by a length. It's still a vector. So this input's a vector and output's a vector. So therefore, this should this is bold. Okay. So they're saying suppose x is a vector in R3. Note that n is not defined at 0. Okay, so n is not defined at 0 because you can't do that. So the largest possible domain for n is R3 minus the point 0. Can't have 0 in there. The range of n consists of all unit vectors in R3. All unit vectors in R3. The function n is the normalization function, that is the function that takes a non-zero vector in R3 and returns the unit vector that points in the same direction. Okay, they also say that sometimes a function isn't necessarily given by a formula, it could just be given by a table. So this is wind chill. So if the temperature is actually 40 degrees, they're talking about Fahrenheit, but anyway, if the temperature is actually 40 degrees, but if it's cold, if it's windy, it'll feel colder. So if it's 5 miles per hour wind, it'll feel like 36. If it's 30 miles per hour wind, it'll feel like 28. So this is not given necessarily by a formula, just this table describes the function. So the input is the actual temperature, and the output is these numbers here, which is what it feels like. I'm sorry, no, wrong, sorry. This is, this is a vector input and a scalar output. So the input is this, comma, this, so it's a vector, or this, comma, this. And the output is this, for example. So it's input is a vector, but the output is a scalar. Okay, here's an example of a scalar input, but we get a vector output. So here we get a vector output. You can see that it's a vector output just by identifying that there are commas here. So that means, if I can get this, that means that the output is a vector. This is a vector. So you're given a t, you get this. The graph of this looks like this. So we're looking at the output. Now this is a parametric equation. In parametric equations, we almost never graph the t. The t is like time, and it's not graphed usually. And all we're looking at is the output as t increases. So as t increases, these two make it kind of go in a circle. But this one is the z variable is always increasing. So it's like a circle, but it keeps going up. So it looks like, they call it a helix or a corkscrew. Okay, here's another example talking about the velocity of a fluid. So we can think about a river or any kind of fluid. Of course, we need to specify the location. Of course, we need to specify a point in R3, but we're also going to be including the time. So we're going to be giving the velocity of at a specific place and at a specific time. So we're going to allow for the velocity to change over time, even at a particular point. So this is a vector input, and it's R4. So we say that the domain is a subset of R4, and the range is going to be the velocity, and velocity can point basically in any physical direction, in any direction basically. So it can be anything in R3 can be the velocity. So we need the I component of the velocity, the j component, and the k component. So this is a vector, this is a function, a vector valued function, velocity, from R4 to R3. And this could be an example. Here's a picture, another picture. So at any particular place you have, and any particular time, you have a velocity. And a velocity points in a particular direction, and it also has like a magnitude. And it's given by this. Given this input, we get this output, which tells us the velocity. Okay, now we're going to call this part the ith component of the output. And we're going to call this part the jth component of the output. And we're going to call this part the kth component of the output. And you can see that each one of these is a function. This is a function, this is a function, and this is a function. And also, instead of calling it the ith component, because we don't always necessarily mean just 3 dimensions, like here we have just I, j, and k, but of course we want to allow for functions beyond just R3 as the output. So maybe we shouldn't call this the ith component, we'll just call it the first component, and we'll call this the second component of the output, and this we'll call the third component, and so on. And each of these is just a function. Is a function, and each one is a scalar valued function. So this just gives you a scalar, right? When you put in x, y, z, and t, you just get a scalar out for just this part. Not the I, just this part here. And this just gives you a scalar output. If you put in x, y, z, and t, in this case you don't need z and t, but x and y, and that will give you a scalar. So this is called the first component function, this is called the second component function, and this is called the third component function. So the component functions are the scalar functions that give us the outputs. So we can say that if f goes from Rn to Rm, and then you see the bold f, so that means that it's vector valued, and that means that m is not 1. So we can think of it in terms of the component functions. So the f1 is called the first component function, and that's here. And f2 is the second one, and that's here. So we have these f1, f2, fm. If the codomain is Rm, then we're going to have m components, and so here we denote them like that. The component functions are scalar valued, and they're scalar valued functions of x, the bold x. So in this case, x, not necessarily, right? We saw that they don't actually have to have all, well, let's say, anyway, they're elements of here, although they may not have all of the x's. We saw this one only has x and y, it doesn't have z and t. Okay? So, so what we get is, so what's going on here? So this is the situation. We have a vector valued function, a bold f, with vector input. These represent the inputs, and the output is a vector. So we could write x, y, z, t, comma, this, comma, this, right? That means a vector, the commas, but we're calling them f1, f2, and fm, right? And they take vectors as inputs, right? This is a vector. This needs a vector to give us x, y, z, t. Okay, so we can write it like this, Or we can even write it like this, where we write out all the elements of the input here, and this is the first component function. Okay, so this is kind of messy, as she says, a morass of symbols, but we could write it out like that. Okay, for example, this function was the length function. Now, its output is just r, so it's not such a great example, I think, because there's only going to be one component function. In fact, no. I guess you can call it a component function, but it seems like it should be multiplying a vector, and we don't even have a vector of any sort. That seems a little strange to use as an example, actually. But, for example, this function, when expanded, becomes this. She doesn't say that those are the component functions. Or, I mean, that this is the component function. Anyway, this seems like a bad example. But let's try this one. So this was start with x and get a unit vector in the same direction as x. We did this part. We did this already. And basically, x is now expanded like that. And then the norm of x is written like this. So we get that, which can also, of course, be written. This means that you divide each component by this. So that's what they did here. They divided each component by that. So the component functions are this one, and this one. So this would be called f1, this would be called f2, and this would be called f3. Or actually they're calling them n1, n2, and n3. Okay, so we sort of explained that, but then she says, although writing a function in terms of all its variables and components has the advantage of being explicit, quite a lot of paper and ink are used in the process. The use of, so now she's saying that vectors kind of like simplify everything. So if you saw this, it's sort of crazy and confusing, maybe more than this. Maybe, right? But anyway, both are true. This is one way. This is another way to write it. The use of vector notation not only saves space in trees, but also helps to make the meaning of the function clear by emphasizing that a function maps points in Rn to points in Rm. Vector notation makes functions of 300 variables look like a function of one variable. To try to avoid writing out components as much as you can, except, okay, so next we're going to talk about visualizing functions. This is an example of visualizing a simple function, just a function. Now I mix up. Sometimes I'll say this is a function of in one dimension or two dimensions. So I don't know which is the right way to say it necessarily, but you could say it's in R2. It's not in R2, but this plane is R2, but the output is just R1, right? This is just R to R. So you could say either way. But anyway, so that's what we think of when we think of visualizing a function. However, here we have a function from R2 to R, which means a function of xy that goes to a scalar output, and here it is. And the way you have to visualize that is you'd say down here is the xy point, the input, and the height is the output. So at different xy's you get a different output, you get a different height. So this is the surface, this is a surface that indicates the output. So we're going to come back to this in a second. Anyway, we're going to learn about what are called level curves, which is, you basically are already familiar with level curves because something basically the same thing as level curves. Like when you look at a map and you get these contours, a contour map. Do they have any pictures? This is a kind of contour map of this. So anyway, if you look at a map of an area, sometimes they'll do that, and those will indicate the different heights. Okay, so maybe this is an example of a topographical map, and you can see these lines, and I think everybody knows what this means. It means that, well, every point on this curve, for example, has the same height. So it's indicating the height of the land. And oftentimes they have like a have numbers on them, and this indicates that every point on this dark line has height like 900 maybe meters, and every point on this dark line has height of 910 meters, and so on. So this looks like there's a that the height is increasing if you walk in this direction. So maybe there's kind of a hill or a mountain here. And here's another picture, topographical map. So here, this is a little bit different, but you can see sort of where the topographical map comes from. So you can see that all the, like this maybe is 800, so everything along here has height 800. Now these are actually what we call the contour curves. So these are not in 2D, right? The other pictures we looked at were just flat. They were just in 2D. But these are supposed to be curves in 3D, right? So those are called the contour curves. So we're going to distinguish between those two kind of views. So here we have what are called the, these are the contour curves. These are called the contour curves, and this is called these are called the level curves. So the level curves are in 2D, right? These curves are in 2D. So the level curves come from, if you stood above here and you look down on it, you would see this picture. So, but nevertheless, these are curves in the plane. This is the plane, so these are curves in the plane, whereas these are curves in 3D. So these are called the level curves, and these are called the contour curves. So how do we do that? We're just taking like a plane of a certain height, like here. We just take a plane of a certain height, and we cut it through the surface, and we ask where does it cut the surface, and that's how we get the contour curve. And then we take a plane of a different height, and we cut it through the surface, and then we ask where does it cut the surface, and that's a different contour curve. And then of course, just to get the level curves, you just look down to get the level curves. And this can help us to actually draw the curve. So what they say is we draw certain curves, special curves that lie on the surface, z equals f of x, y. These special curves, called contour curves, are the ones obtained by intersecting the surface with horizontal planes. So how do we define a horizontal plane? We say z equals c. That gives you a horizontal plane. So a particular c for various values of the constant c. And so we get different contour curves with different c's. Some contour curves drawn on the surface of example 10 from this example are shown in figure 211. So here, these are some contour curves. Then they say if we compress all the contour curves onto the xy plane, in essence if we look down along the positive z-axis, then we create a topographic map of the surface that is shown in figure 212. So that's this one here. These curves in the xy plane are called the level curves of the original function f. So this is our function f, and those are the level curves. And they say this can help us to graph the function z, to graph it, just like when we look at this topographic map, we can guess that there's kind of a hill here. In the same way, we can use these level curves that we're talking about to help us graph our surfaces. So they say we can, what do they say? We construct a topographic map in R2. So we do this by finding the level curves of f. So we find the level curves. So how do we do that before we go on? Let's do that. Let's suppose that this is our function. Okay? So what we do is we just set this equal to different values of z, or different values of c. And then we can get different level curves. So if we set this equal to different values of c, so here, if c equals -5, then what do we get? 4 minus 5 is 9. So we get this equation, x squared plus y squared equals 9. But that's the equation of a circle. That's the equation of a circle of radius, the square root of this, so of radius 3. So that will be one level curve. And what that means is that every point on that circle in the xy plane, every point on that circle will get mapped to a height of -5. Okay, let's try this one. When c equals 3, so we're cutting the surface with a horizontal plane of height 3. So then when we put 3 in for c, we put 3 in for c here, we get this. So what is this? This is a circle of radius 1. So every point on that circle will get mapped to a height of 3. So but anyway, each of these generates a level curve, okay, which can help us to visualize our function. So actually, if we do that, we get these circles. So this is c equals 4, this is c equals 3, c equals 1, c equals, and so on. So we all the points here, actually there's only one point, gets mapped to a height of 4. All the points on this circle get mapped to a height of 3. All the points on this circle get mapped to a height of 1. All the points on whatever circle get mapped to a height of 0. And all the points on this circle get mapped to a height of -5. So we can kind of get this picture, and then from that we can figure out that this is what it looks like. So they say, first construct the topographic map in R2, by finding the level curves of F, then situate these curves in R3 as contour curves. These are the contour, these are the level curves at the appropriate heights, and finally complete the graph by kind of figuring out what it looks like. Okay, so let's define these carefully, these two ideas of the level curve and the contour curve. So first of all, you should remember the level curves are in R2, and the contour curves are in R3. So anyway, suppose that f is a function from R2 to R. It's scalar valued because this is just R, of 2 variables because this is R2. The level curve at height c, we choose a height, of f is the curve in R2, defined by this equation. So c is just a number now, so this is just a function with 2 variables. So that's a function in R2, where c is a constant. In mathematical notation, the level curve at height c will be a set of points in R2. These are sets of points. These are points in R2. Which points? The set of points such that f of xy equals c. Okay. On the other hand, the contour curve at height c of f is the curve in R3, defined by the 2 equations, or really it's just one equation, but they say 2 equations. Anyway, it's the equation, it's the set of points in R3, so it's in R3, contour curve R3, defined by the equation, so for a particular height c, is defined by the equation here. Okay, so, but this equation is basically in R2, but these points are in R3. So I guess that's where they say the z. So z is equal to c, so you put that c here, and then you find the set of points which satisfy this. That gives you a whole bunch of points, all with the z-coordinate z. And that's the contour curve. That's these 3D curves. Now, instead of using horizontal curves, we can also slice the surface with vertical curves. And we can use vertical curves where we fix x. Like here we fixed z was equal to c. We could also fix x is equal to c. Or we can fix y is equal to c. And in both those cases, the last two cases, when x is equal to c, or if y is equal to c, those give us vertical planes, which will also cut the surface. And those are called sections, a section of the graph. So you choose a particular c, so x equals a particular c, that's a particular vertical plane. Which vertical plane is it? It's the vertical plane that has the x-coordinate is c, and y and z can be anything. And then, do they have a picture of that? There's not a picture of that, but anyway, that will give you a vertical plane, and then you'll get a set of points that cut that intersect with the surface, and those are going to be in 3 dimensions. And then you can also do it when y equals c instead of x equals c. You also get a set of points in 3 dimensions, and those are called the section of the graph of f by the plane y equals c, and this one is called the section of the graph of f by the plane x equals c. So sections are 3-dimensional, contour curves are 3-dimensional, level curves are 2-dimensional. Okay, here's another example. We have a function from R2 to R, this one, and we can ask what are the level curves. And we do the same kind of thing here. We set c equal to different things, and we get different equations, and those equations apparently look something like this. So here's a c equals 4 equation. It also has this part, and this part, and this part. Here's a c equals -1 equation. It also has this part, and so on. So, so those are the level curves, and that's supposed to help us somehow to figure out what this looks like. So I guess it does, because this has a height which is not as negative as this one. So maybe they helps us to see that it looks like this. Maybe. I guess. Is this the right one? Yeah. So this could help you to draw this. Then they do another example. They say, how about this one? Or sorry, this one. So what does this look like? So the level curves look like this. They do it. They get these are the level curves. So somehow, so E comes in there, but it's E to the C. So then you can ask, what are the graphs of this and this and this in R2? And I guess they look, yeah, I guess they're circles also. So they're circles. So these are the circles. So maybe that gives you some idea of what the graph of this looks like. So this gives us some idea of what it looks like. So when c equals -5, it's so these points all get mapped to -5. These points all get mapped to a height of -1. These points all get mapped to a height of 0. These points all get mapped to a height of 1. These points all get mapped to a height of 3. So it looks like it's kind of like a funnel. Or it could be a parabola, kind of a 3D parabola. Or it could be kind of a funnel. Depends if there's a smallest, lowest height or not. Now they say that if we switch from Cartesian coordinates to cylindrical coordinates, we didn't actually cover that, I don't think. But we covered a little bit of polar coordinates, but I don't think we did cylindrical coordinates, but you could switch to cylindrical coordinates, and they say that these are both called surfaces of revolution obtained by revolving different curves. Anyway, so this is apparently the shape of the other one. We're not going to go into surfaces of revolution. That's a part of calculus, and we're also actually probably won't use cylindrical coordinates. But anyway, this is the shape. Okay, so now we want to define what we mean by the graph of a function from Rn to R. So we've talked about functions from R2 to R and what we mean by the graph. If we go back and look at that, this was the definition. Before we talked about contour curves and level curves, we said this, that the graph is, for this one, for R2, was x comma f of x. But remember, x is two-dimensional, so we have like an x and a y here, so x comma y comma, but remember f of x is just a scalar, so it's x comma y comma one more, in other words comma z. So the graph of a function is a surface. We said that we've been working with that idea. The graph of a function from R2 to R is a surface, and this is what we mean. This is the set of x, y, z points that give us that surface, because a surface is a set of x, y, z points. So now we want to say, okay, well, let's not limit our definition, or let's extend our definition from R2 to R anything. Of course, when we do that, we can't really visualize it anymore. It's not a physical surface anymore. But anyway, if we have a function from Rn to R, we'll say what we mean by the graph, similar to what we just showed. In fact, it's the same thing. It's x comma f of x. But remember now, this x is in Rn. So, and then this is a scalar, so this is one more coordinate. So we're going to have n coordinates here plus one more. So we're going to have n plus 1. So if f is a function from Rn to R, then of course we need to graph it. We need we need more than n dimensions, right? Just like when we were just talking about from R2 to R, it wasn't in R2, it was in R3, right? This was a surface in R2 when this was 2. I'm sorry, it was a surface in R3 when this was 2. Okay, so it's going to be something in Rn plus 1 if this is n. So that's what it says. So it's a subset of Rn plus 1. This was the surface was a subset of R3, right? It wasn't all of R3. It was just a set of points, the surface in R3. So this is going to be a subset in Rn plus 1. So it's going to be these. There it is. And x is in, they say in here, but this is just some subset of Rn. So x is a set of points in Rn. And then we get the surface sort of above it, but now we're not talking about a surface, but we get a bunch of points in Rn plus 1. And that we say that this is the input, this will be the output from that input, and we tack them together, we get the input comma the output. That's the point, that's one of the points in the graph. So she says that the compactness of vector notation makes the definition of the graph of a function of n variables exactly the same as in 1. Okay, then we can also talk about the level set at height c, even for this n-dimensional situation. So remember, the level set was a set of points in one dimension less than the surface was, or than the graph was. So the level set at height c is a set of points in Rn, not in Rn plus 1. The graph is in Rn plus 1, but the level curve is points in Rn. All the points that get mapped to that height c. So this makes it possible to get some geometric insight into functions of 3 variables. So if we're talking about functions of 3 variables, then we're going to have the output variable, which is one more variable. So we actually have 4 variables in total, so we can't graph that. But we can graph the level curves because they will be just in 3 variables. So here's an example. Here's a function from R3 to R. So the graph is going to be in R4. And so we can't do that visually, or physically, I should say. But we can think about the level curves for this thing that we can't visualize. And those are going to be the set of values, x, sorry, that's the graph. The level curves are going to be the set of values x, y, z for a particular c that solve this equation, right? So we can see that the level curves, this is a parallel, this is a plane, right? For a particular c, this is a plane. So with different c's, we get different planes, but they're all parallel, right? You can see that, like if you say what the normal vector to the surface is, you can see that they all have the same normal vector. So they're all parallel. So so those are the level surfaces. I guess we wouldn't call them level curves anymore, but level surfaces. But I think actually they do call them level curves. But anyway, whether we call them level curves or level surfaces, so all the points on this plane get mapped to the same z value. Get mapped to the same output, and all the points on this plane get mapped to the same output, and all the points on this plane get mapped to the same output. So I don't know if that gives us any insight or zero insight, but we can do that. And this is called a hypersurface because, the graph of this is called a hypersurface. They use hyper when you go out of 3 dimensions. So this would be out of 3 dimensions, so they call it a hypersurface of R4. Okay, so you may remember that if you have a shape like this, this is not called a function, because if you have a point here, x1, it gets mapped to this height and to this height, so that's not technically called a function. Of course it is a curve, but it's not a function. So we've been talking about functions. Now we want to sort of generalize, say, well, instead of just like, we've been talking about surfaces of functions, but we can also just talk about surfaces in general, not specifically when it's a function. So for example, this surface here is a surface of a sphere, but it's not really a function. It's not technically a function, because if you take one value of one point in the domain, which would be in the xy plane, and you ask, it could get mapped to here or to here, so that's not good for a function. That's not technically called a function. So not all curves in R2 can be described as a graph of a single function of one variable. So a circle is not, this is also not a function, right? You go from here, take this point, you can go to here and to here, so that's not a function. The analogous situation with surfaces in R3. Frequently a surface is determined by an equation of this form, and it would not necessarily, so they use the word equation of the form, so not function, not necessarily a function. So here's an example. A sphere is a surface in R3 whose points are all equidistant from a fixed point. So this is a sphere. It's the set of all points here that are the same distance from this point. if the center happens to be the origin, then this will give you the equation. It's x, because remember this means the distance from x to 0. But of course you can rewrite it like this. So this is the distance from x to 0 is a. Right? So the set of all points whose distance from the origin is a is some sphere around the origin, where a is, of course, needs to be a positive constant. Otherwise you won't get anything. And then again, if this is R3, then if you rewrite this, looks like this, and you can see clearly that it's a sphere. And if you want to do something that's not centered at the origin, you just do this. So this is that the distance from x to x0 is equal to a. So this is x0. So you just get all the points that are at distance a from this point. And when you expand this one, it looks like this, which is the equation for a sphere around that point, x0. And they say there's no way to solve that equation, this equation maybe here, for z uniquely. So you get this, you try and isolate z, and we take the square root. We have to make a choice. Do we mean the positive square root or the negative square root? Because otherwise we'll get two values if we don't decide on one of them. That means, you know, you get a number like 9 as the sum of all this stuff. So 9, which z is it? Is it -3 or 3? So if it's both, that's not a function. So you have to decide, I mean the positive square root or I mean the negative square root. So that means you're deciding, I mean, you know, the top part of the sphere, or I mean only the bottom part. So just the bottom part of the sphere is a function, or just the top part of the sphere is a function, but together, when you put them together, that's not a function. Okay, but now they do a big trick. I guess it's a trick. They say, of course, the graph of a function of two variables does describe a surface in the level set sense. Okay, the last thing in this section is I just want to cover this statement here. She says the graph of a function of two variables is a surface in R3. Okay, so we know that if you have a function of two variables, it's going to be a surface in R3. And then she says, you can also think of that as the level set of a function of three variables. So what is she talking about? So let's go back and see. So here we were talking about the fact that this doesn't define a function, but if you separate it into these two, you get two functions. Okay, then she says, suppose we have this, then of course we can rewrite that like this. Right? And then now we can think of this whole thing here on the left-hand side as actually a function of three variables. And remember, the situation was just that we had only two input variables. But now we can say, let's just consider this by itself alone as some function of three variables. So suppose we define a function like this. So we have this, and then we define this as capital F. So we just define capital F to be this. So here, kind of capital F is a function of three variables. Now this can, capital F of x, y, z, we could think of the level sets for this function. So the level sets are going to, remember that the graph of this would be in R4, right? Then we can also talk about the level sets and, or the, what do they call them, level curves? Level curve or level set is in R3. And what about the contours? Where are they going to be? They're going to be in R4. The contour curves are going to be in R4, just like the graph is in R4 for this capital F. But the level sets are in R3. Now, the original situation was this. So that means if we're talking about this capital F, we're talking about setting capital F equal to 0 to reproduce this situation. But when we're thinking about it as capital F, we're talking about the level sets of capital F and the particular level set where C is equal to 0. So the particular level set of this, when C is equal to 0, is our original function. So now, with that understanding, let's read this first sentence again. The graph of this function of two variables. Now here, they're assuming this is a function of two variables, is a surface in R3. Okay, we've been talking about that a lot already. And it is also a level set of a function of three variables. So we showed that if we do this and call that capital F, then the graph of this is the level set of this. Okay, it's a little bit confusing. Then she says, however, not all level sets of functions of three variables are graphs of functions of two variables. So what she means there is that suppose you have a function of three variables. If you consider its level sets, they won't necessarily be functions of two variables. You can go one way, but you can't go the other way. What I mean by that is, if you start out with a function of two variables, like this, then you create a function of three variables by doing this kind of thing. Then the level set of this one, the specific one where where C is equal to 0, is a function. So the level set of this particular capital F, when in this case this equals 0, when C equals 0, that will be a function. So for this function, there is a level set that is a function. However, not every function of, for example, three variables will always have a level set that is a function. Okay, this seems very technical, and I'm not sure why we need to know it, but that's what it says. Okay, it is interesting though to see that you can start with a function of two variables and construct the kind of corresponding function of three variables by doing this, by taking the z over to this side, and you really have kind of on the right hand side you'll have something with three variables, and you can call that a function of three variables. And then you can consider the original function as a level set of that of this function. This function is in three variables, but it has a level set, of course, in two variables, which equals the original function. So that's kind of interesting, and that may come up somewhere as useful. But I'm not quite sure of her emphasis about the fact that whether it's a function or not. Right? Remember, by the word function, we mean that you don't have, going all the way back to the beginning of this section, you don't have like this x here going to two things here. So this x only goes to one thing. This one only goes to one thing. This one only goes to one thing. These two happen to go to the same thing, but we don't have this x going to two places. That's what we mean by a function. Okay, with all of that, that's the end of this section.